Hello, everyone. Welcome back to Toronto Machine Learning Summit Annual Conference 2021. My name is Nadia, and I'm a senior machine learning engineer. And today I'm really excited to be here and to have the opportunity to introduce one of our amazing speakers. Before starting, I would like to remind you that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speaker after the presentation. Our speaker for this session is Mikhail Yurochkin. Mikhail is a research staff member at IBM Research and MIT-IBM Watson AI Lab in Cambridge, Massachusetts. His research interests are model fusion and federated learning, algorithmic fairness, application of optimal transport in machine learning, and Bayesian nonparametric modeling and inference. Before joining IBM, he completed a Ph.D. in statistics at the University of Michigan, where he worked with Long Nguyen. He received his bachelor degrees in applied mathematics and physics from the Moscow Institute of Physics and Technology. Please join me in welcoming Mikhail Yurochkin.
Nadia, thank you for the introduction, and thanks everyone for tuning in. So today's topic is algorithmic fairness, and more specifically individual fairness. So I will first give a brief introduction to fairness in machine learning in general, and then we'll dive into like specific methods that we developed for achieving that fairness in practice. So, well, first of all, just to I guess to remind everyone, is machine learning is used quite a lot in applications. So it's used in healthcare, in criminal justice, in finance. And there is a lot of evidence that oftentimes, not careful usage of machine learning leads to biases. So it's despite sort of algorithm conceptually being, these automatic entities, they pick up human biases from the data, and they can, exaggerate or maintain sort of the human biases that already exist in the society. The same happens even in banking. So why am I mentioning banking is because there are actually legal regulations that try to prevent bias of using algorithms in finance. So for example, the Equal Credit Opportunity Act in the United States. But despite of that, the recent study from 2019 shows that there is still a big difference in rejection rates across different races, and there are billions of dollars in race premiums. So, well, despite the problems, I think it's important that we try to fix them. So I think algorithms can be improved. We can introduce fairness into them, and hopefully fix them in a shorter time span than it takes to sort of correct the societal biases. So first of all, so what is a fair algorithm? So one of the popular definitions of fairness is what's called the group fairness. So the key idea is that the algorithm should be equally good on groups of individuals. So here we have two groups of individuals. So, and then let's say on the first group, the algorithm is correct 75% of the time. So, it's only wrong 1 out of 4 times. And on another group, it's wrong 3 out of 4 times. So this means that the performance, for one group, the algorithm is actually performing well. For another one, it's performing quite poorly. So this is a violation of group fairness. So to satisfy group fairness, you want an algorithm that performs equally well on both groups of individuals. So speaking sort of mathematically, so this usually relates to these notions of independence. So if you have, let's say, y is a true label, a is a protected attribute, and y hat is a prediction. So we want statistical parity is one version that says we want our prediction to be independent of the protected attribute. So for example, we want the loan approvals rate to be same for different races. And the other one is basically an extension of this where we additionally condition on the true label. And there is quite a lot of work on group fairness. So there are techniques out there that can enforce it. But there are some, as I'll show in this talk, there are some disadvantages of group fairness. And that is why we are considering individual fairness. So on a high level, individual fairness says that we want algorithms to treat similar individuals similarly. So it is sort of individual. So we want to not just take care of groups, but we want to take care of every person. So a simple example. So suppose we have 2 applicants for a loan. So Ryan that earns 50,000 and lives in a predominantly white zip code area, and Terry that also earns the same amount of money and lives in a predominantly black zip code area. So if, for example, Ryan is given a loan, but Tari is denied a loan, this is a violation of individual fairness because, well, these two individuals only differ in their name and sort of their zip code, but otherwise their incomes are the same. So individual fairness requires that the decision for both of these applicants is the same. So either both are approved or both are denied. So again, more formally speaking, so individual fairness was introduced by Cynthia Dwork and co-authors in 2012. So it is type of a Lipschitz continuity condition. So specifically, if let's say we have a model H that takes some inputs, produces some predictions. So H of X is a prediction. So we want to make sure that the difference in predictions is bounded by the difference in the inputs. So here the difference in inputs is measured by a fair metric. So for example, Ryan and Tari in the early example, they were similar. So the dx of x1 being Ryan and x2 being Tari should be very small. So then this condition says that, well, because the dx is very small, the dy between the outputs, so decisions on those two individuals, should also be very similar. So this is the key idea of individual fairness. So why do we study individual fairness as opposed to maybe group fairness that I mentioned? So let's consider a simple example. So sentiment analysis, we want to classify words as positive or negative. The positive words are admire, adorable, so on, negative, aggressive, nasty, and so on. So it's a pretty simple task actually by these days. So we can use deep learning, we can use war embeddings. It is very simple to achieve 95% test accuracy without much tuning or anything. So does it mean we solve the problem? Well, let's consider how the system can be used in practice. So now we use the system to evaluate the sentiment of maybe sentences or like different texts or in the wild. And sometimes the text contain names of people, for instance. And then what is the sentiment of a name? What will the system do when it sees a name? And so let's say we have these names which are more typical among the European American population, so such as Adam, Ryan, and so on, and the other names which are more typical among the African American population, so Tyree, Leroy, Alonso, and others. So let's compare what is our algorithm doing with the names. So here we are basically plotting these box plots of the sentiment scores for names, which are grouped by sort of which populations are more typical at. And so we see there is a big gap. So the names for the sort of more white-sounding names have a lot larger sentiment scores than the more black-sounding names. Well, this is a violation of group fairness because even if you compare these two sets of names as the two groups, then there is a gap. So we can fix this. So suppose we use the group fairness and we fix it. So now on average, the sentiment of names for both groups is the same. But did it solve the problem? Is the algorithm fair now? Well, the name Ryan still receives a very high sentiment score. The name Tyree receives a very low sentiment score. So from the perspective of Tyree, the algorithm is still quite unfair. So this is an example of sort of group fairness being satisfied, but really the intuitively fairness has not been achieved. And so using our one of our individual fairness algorithms, we can achieve this different result where actually all of the names, they have very similar sentiment scores, very close to neutral actually. So now all pairs of names are comparable. So Tyree, Ryan, all of them receive similar sentiment score. And at the same time, the accuracy is not compromised. So our original accuracy was 95%. So now we still maintain an accuracy of 94%. So we just paid a small 1% price for actually, making sure our algorithm will not cause biases when at deployment. So how did we achieve that? Well, so we first I will introduce this notion of distributional individual fairness that we work with. So sort of the motivation for this is the original one being a little bit more challenging to use in practice. So, but this one is conceptually has the same motivation behind it. So the distributional individual fairness is essentially says that we want the difference between the outputs on average to be similar as the usual individual fairness, subject to the individuals that we evaluated on are similar to the original one. So in other words, so let's say we have a collection of data points and we have a marginal distribution P of X. So we want to find a map T. This map tries to expose the violations of fairness. So the map T tries to modify the input size to xi primes such that the difference in the outputs is maximized. And if you can find such a map, then it means that actually algorithm is unfair because there exist similar individuals to the ones we observe that cause violations of fairness. And if you cannot find it, then everything is good. So this definition is motivated by some earlier studies in social science. So economists in 2004, they studied racial bias in the US labor market. So, well, first of all, they needed a sort of, distribution of inputs. So for that, they responded to job ads in Boston and Chicago newspapers with fictitious resumes. So basically their resumes for the axis, the data points. So how do we sort of, this map T, as I mentioned, it tries to expose violations of fairness. So how did they do it? Well, of course, they did it sort of practically rather than mathematically. So they essentially randomly assigned African-American or white-sounding names to the resumes. Otherwise, the resumes were exactly the same. And so then they measured the difference in the response. So basically, whether the resumes that have white-sounding names and the resumes that have African-American sounding names, they receive the same amount of callbacks. And so it turned out that not at all. So the resumes assigned white sounding names is 50% more callbacks for the interviews. So essentially, back in 2004, they conducted this experiment manually, and they evaluated something that today we formalize in this notion of distributional individual fairness. So now that we sort of talked about what distributional individual fairness means, so it's a quantity, right? So how do we actually how do we train an algorithm that achieves fairness? So in other words, that has a small value of distributional individual fairness violation. So first, just to recap how generally we do it. So when we train an AI model, so we train an algorithm accurate on the data that we have. So we observe data, we update parameters to minimize the prediction error, we repeat. So basically, this is a standard process. So here, the overall idea is slightly different. So we want to train an algorithm that's accurate on the data that we observe, but also on all possible similar data. So we don't just consider what we see, but we also consider maybe modifications of resumes by changing the names, gender pronouns, and so on. So we observe data, then algorithmically we generate similar data where algorithm performs differently. So this allows us to evaluate the distributional individual fairness. So then we update parameters to minimize prediction error and to minimize the DIF. So remember, the small value of DIF implies the fair algorithm. And so then repeat. So more specifically, so our objective function will be the loss function. So the usual, classification error. And we use our DIF value as a regularizer. So there is a coefficient draw that kind of can trade off, how much we want to pay attention to minimizing the classification error versus how much we want to pay attention to being fair. So one remark is that sort of for those maybe also familiar with this idea of adversarial robustness, so the original formulation of DIF required us to find that map T, and maybe it's not quite clear how to find it. Indeed, it's a very hard infinite dimensional optimization problem, but appealing to the duality theory, we can rewrite DIF as its dual, and then it's actually pretty easy to implement. So here, the idea of the dual is essentially to perform an optimization to find x prime, such that the difference between outputs on x and x prime is big, while x and x prime are similar. So this is pretty similar to the idea of adversarial robustness, where we perturb images. We try to find visually imperceptible changes to images to trick or fool the machine learning model. So here, instead of visually imperceptible, we want the changes that are small in the fair metric, and then we again want to change the output of the model. So another important part is that all of this can be written as an expectation, and what practically it means is that we can use stochastic optimization. So we can easily implement it with PyTorch, TensorFlow, and train a model using popular optimizers, stochastic gradient descent, Adam, and so on. So this is all quite straightforward to do. So let's look at an example. So we'll consider this simulated data set to begin with, where the points on horizontal lines, we consider them similar. So this is just for the sake of an example. So everything that's has the same y values, we consider them similar individuals. And so we'll have a biased training data. So of course, the true decision boundary, the optimal decision boundary is not constant on horizontal lines. And we'll use our regularizer to correct the bias. So here is the original data set. So the blue points are class 1, the red points are class 0. And so we see that sort of the best decision boundary here is the one that is totally not sort of constant along the horizontal lines. So we can see these individuals which receive absolutely different predictions, but they are on the same horizontal lines. So now if we add the DIF regularizer with a smaller value of rho, so now we get something that's more horizontal. And so we can continue adding the increase in the regularization strengths for the DIF regularizer, and we can achieve sort of more horizontal decision boundaries. Eventually, it's perfectly horizontal. Of course, in this example, so we see that trying to enforce fairness also sacrifices some amount of accuracy, but it doesn't always have to be the case. And as we'll go into the real data examples, I will show that sometimes enforcing fairness can also improve the performance. So first, a practical example is the toxic comment classification. So the goal of this application is we want to ensure sort of inclusive and safe discussions on online platform, which are free of insults and do not try to reduce the voices of some minority groups. And so for that, the common thing to do is to train an algorithm that tries to identify whether a given comment is toxic or not, and then implement some type of moderation. So how do we measure individual fairness? Well, first of all, the problem is that in this data set, in the training data, because of historical biases in the society, the certain words, they often appear in the context of negative comments, in the context of toxic comments. So for instance, the word gay in the training data oftentimes is present in a comment that is also toxic. As a result, the model that is trained in a regular way will think that the word gay is a good predictor of being toxic, and then if you ask it to make a prediction on a phrase, some people are gay and some people are straight, so it is likely to say that the first phrase is toxic and the second phrase is non-toxic, although both phrases are basically just neutral. And in order to measure individual fairness, so we sort of check that idea. So in addition to gay and straight, we have these 50 identity tokens, so which relate to religion and gender and like other things, and then we kind of replace those tokens. So if you have a test comment that says some people are gay, so we'll replace gay with straight, with Christian, with Muslim, with male, female, and so on. And then we'll check that predictions on all 50 variations are the same. So then we call this prediction consistency. So if they're the same, then the prediction is consistent. And so here we look at the balanced accuracy, which is just a measure of performance, and we look at the prediction consistency as a function of the regularization strengths that we sort of the coefficient in front of the DIF regularizer. So our algorithm called Sensei, so we see that if we increase the regulation strengths, we do lose some amount of accuracy, not a lot in this case, so around 1 to 2%, but we quite significantly improve prediction consistency, so we can improve it by 15%. So this is still a trade-off with accuracy, but the amount of fairness that we gain is quite large. The second example is achieving individual fairness and occupation prediction. So this is a task that can be maybe used by like recruiters to help them find candidates, because there are so many profiles online or LinkedIn. So perhaps there could be some systems that help to identify good candidates for a job. And so the data set consists of 400,000 textual bio descriptions, and the task is to predict one of the 28 occupations from a bio. So, and here, so again, in the data set, some of the occupations, so for instance, lawyer, in the data set, there are more males than female lawyers, and that opposite goes for, let's say, paralegals. In order to measure individual fairness here, we, again, the same idea, so we measure prediction consistency, but here we modify the names and the gender pronouns in a person's biography and see if the prediction changes or not. So here we increase regulation strengths, and again, on the right plot, we see that the prediction consistency improves in this problem, so the fairness is improved. If you look at the accuracy, we see that it's not hurt. So it even a little bit improves, I mean, not by really much, but this is an example of when enforcing fairness can also help at the test time. So for example, think of, let's say there is, in the computer science, there is currently, there are not a lot of female researchers. So if you train a model on a past historical data, like especially in the past, there were even fewer of them. So the model might think that sort of any gender identification is like a male gender identification is a good predictor for a person being a computer scientist. But then as we go into the future, the data changes. So maybe now there is a bigger proportion of female computer scientists. As we go further, hopefully there will be even larger proportion of female computer scientists. in which case using gender to predict a person being a computer scientist is a bad idea, and in which case fairness can actually improve the accuracy. And lastly, I wanted to mention that so these experiments were done actually with quite large-scale models. So we used BERT to extract useful embeddings from the text, and trained like an additional neural networks on top of it. So this is because, as I mentioned earlier, the algorithm is amendable to stochastic optimization, so it can be deployed with large-scale modern models. Okay, so next I wanted to talk about post-processing for individual fairness. So we've talked about training, right? So how do we train a model that is fair? This is technically, so training a model that's fair from scratch is usually the best thing to do. But in practice, oftentimes, the companies already have a system that's been deployed. So it sometimes consists of many different components, and a lot of time and money has been spent to make the system work. And so now if to achieve fairness, retraining all of that is the right thing to do, but it takes a lot of time. So instead, perhaps the more sort of a short-term solution is to post-process. So what does it mean? So we do not need to retrain the model. So we just take an existing model as is that we already use in production. So then the post-processing methods are usually quite fast and they're easy to implement. We do not need to know the parameters of the model. So if it's an API call, it's still fine. So all we need to know is the output. So, we give a model an input, it produces some output. That's all that is needed. So how do we do post-processing for individual fairness? Well, the key idea is to represent individuals as a graph. So, and then once we represent individuals as a graph, we can quantify fairness with the graph Laplacian quadratic form. So it's a pretty standard technique in the graph signal processing, but here we show that it actually can be adapted to do post-processing for individual fairness. So as an example, let's consider these 5 job candidates. So let's say the job application requires knowledge of Python. So Alice, Dave, and Charlie, they all know Python. So they're all qualified for the job. But let's say the current algorithm only chooses to consider Dave and Charlie and rejects Alice. So this is a violation, again, of individual fairness because Alice and Charlie, they have exactly the same qualifications, and Alice and Dave have similar qualifications, both know Python. So, so here is the link between the Alice, Charlie, and Dave. So the line is an edge in a graph. So we can think of these 5 individuals forming this little graph where Alice, Charlie, and Dave are all connected. We're an edge with different edge weights versus even Bob, they are kind of disconnected from the remaining ones. So once we look at this as a graph, so what does it mean to be individually fair? Well, it means that we want, for those individuals that are connected by an edge in a graph, we want the prediction to be the same. So that's the idea. So in order to achieve this, so in order to post-process the predictions of this algorithm, we solve this quite small, simple optimization problem. So let's say the y hat is the original prediction that came out of a model. So L will be a graph Laplacian. So the term on the right is a graph Laplacian quadratic form. And so the F is what we're trying to find. These are post-processed fair predictions. So there are 2 terms. And so the first term, F minus y hat squared, it's basically says that, okay, we believe our algorithm, our y hats are actually accurate. So we don't want to change them too much. That's number 1. So number 2, at the same time, we want to achieve fairness. And the fairness is mentioned by the graph Laplacian quadratic form. So we want to penalize individual fairness violations. So actually solving this optimization problem is extremely simple. It is a closed form solution. So there could be many ways to implement it. And so we have a recent paper at NeurIPS, which actually shows that it's, it's very fast, very easy to implement, and it actually works really well on the same application that I've talked about before. So on a, occupation classification and toxic comment prediction, these algorithms work pretty well. Okay, so next we'll talk about something that's called subgroup fairness, and so I'll explain what is it. So just recently, a couple of years ago, so this story happened with the Apple Card that was created in collaboration with Goldman Sachs. So one of the entrepreneurs sort of tweeted that his wife received 20 times less credit limit than he did, despite sort of other considerations that make it so that they should actually be getting the same amount of credit limit. So, and so what happened really, this actually prompted an investigation into Goldman Sachs. And so, after that, if you do some Google searches about Goldman Sachs women credit, Apple women credit. So we can see that there have been some sort of damage done to the reputation, besides just creating the bias situation and discriminating people. So while we don't know sort of what happened for sure in this case, of course, but one possible explanation is what is called a subgroup fairness. So subgroup fairness is something in between the group fairness and individual fairness. So suppose we have this case where the group fairness is actually satisfied. So we have two groups of individuals. So there's 50% rejections for both groups of individuals, and this is generally something that's required by this Equal Credit Opportunity Act that I mentioned. That, let's say, the approval rates or the credit limits are similar across different groups of individuals. So let's say across male and female. So this is a current regulation, so it is likely that it's been satisfied. But now, what if you look at this population a little bit more carefully, and then turns out there are actually subgroups within this. So let's say on the left there are males, on the right there are females, but then there are also some of them live in a wealthy neighborhood, some of them live in a low-income neighborhood. And so we see that actually amongst the right group, the individuals that live in the low-income neighborhood were all denied, versus for the group on the left, it was not the case. So we see that there is a subgroup fairness violation. So when we consider the population on a more fine-grained level, then again, the fairness is violated. So one way to fix it is, of course, to use group fairness, but then we need to be very careful, because we need to really think about all the subgroups in advance and define them carefully, obtain the subgroup labels and so on. And once we have too many subgroups, then it's actually it's pretty hard to use the group fairness methods to deal with so many subgroups. And so if you think about it, so the group fairness says let's say we have two groups, right? And then we start partitioning them into subgroups, and then in the limit, the subgroups are so fine-grained that every individual is their own subgroup. In which case, we are actually solving individual fairness problem. And so that's what we tried here. So we showed that individual fairness can be used to enforce a subgroup fairness. And so the real data example we considered is this adult data set, where we predict individuals' income based on census data. So here we used our earlier algorithm sensor, and we compared it against a baseline, which is just naive training, and one of the group fairness methods, adversarial debiasing. So here we again measure this sort of prediction consistency. So here there is this there is a variable in the data set which says if someone is a husband, a wife, or single, essentially. So it's super correlated with gender. And suppose the data scientists might have overlooked the existence of that variable and only took care of gender, but forgot that there is a variable called the relationship status. So in order to check whether different methods are actually consistent or not, so we change this variable related to relationship status, and which is called spousal consistency, and then we again check whether the prediction changes or not. And so as we can see that the sensor plus explore, it's one of the variations of the method, and sensors, they achieve pretty high spousal consistency. They also achieve pretty good metrics. So the right four metrics, all the four gaps in the table, they correspond to group fairness. They also achieve good group fairness metrics. And versus baseline, of course, it's not being super fair, but being the most accurate. While adversarial debiasing is one of the existing group fairness techniques, it does mitigate some of the group disparities. So you can see the gaps are better than the baseline, but it actually makes the spousal consistency even worse. So somehow the algorithm learns to use this variable that's correlated with gender to satisfy some of the constraints that we place in it. Okay, so this is this example of subgroup fairness and how we can use individual fairness to achieve it. So now I just would like to make a couple of announcements. So with colleagues at IBM, so we are developing a Python package that will hopefully be ready next year. So we call it InFairness. So it's just a very, very small preview so far. But basically, I've talked about all these algorithms and presented some of the key algorithmic details, some equations. And we actually have a code available online, but it's a research code. So when we were working on a paper, we wrote a code to test our method. But of course, I understand that it's not very easy for anyone to use. So the goal is to have something as simple as scikit-learn, where whoever is interested in achieving fairness in their application, they can just import something, some methods, and start training, and then get some results quickly without diving into all the sort of details and the mathematical aspects of the algorithms. So far we support some simulation experiments. So this experiment is similar to the simulations I showed earlier, but now sort of it's, from inference trainer, we import a trainer and then we train. So it's a lot easier than dealing with a quite messy research code. So this will be open source, and hopefully everybody will be able to use it and to try it out for their problems. The other announcement is we're also working on releasing some demonstrations and interactive visualization tools. So what I'm showing you so far is not yet interactive, but it's actually, we are thinking of interesting ways to let people explore what fairness means in different data problems. So this hopefully wouldn't require any knowledge of programming at all, but we plan to release it as some sort of, web tool where people can explore and play. So here we are comparing on this adult data set that I've used in an earlier data example. So we're comparing a fair and unfair model. And so we sort of explore how the model decisions change as we consider age 32 Black male working a full-time job. So remember here we were predicting whether the person earns less or more than 50,000 a year. And so here, as we move along x-axis, we kind of change the person to appear more or less as a white individual. And on the y-axis, we change a person to appear more or less as a male. And so we see that the unfair model is actually very easy to change its decisions. So if we move more towards being white, it very quickly decides that, okay, now this person earns over 50,000 a year. And the similar happens with the male direction. So for fair model, we see that it's not very sensitive. So the decision, so 0 means that the decision doesn't change, essentially. So as we change the individual in this sort of directions which are not relevant to the prediction task at hand, the fair model keeps its prediction as it is, so meaning that it is individually fair indeed. Okay, so now in the remaining time, I'll talk a little bit about a fair metric. So remember how we talked about trying and Tyrese, that I said that they're comparable individuals, similar individuals. So that was, of course, a toy example. So in practice, we want to, make such decisions sort of algorithmically. And it is actually pretty hard. So it requires, a lot of subject expertise to cover all possibilities. It could be time consuming. For some data types, even with expert knowledge, it could be really hard. So are the two images similar and so on. So that's why we developed some methods for learning a fair metric from data. So the idea of a fair metric is to write a fair metric as a Mahalanobis distance. So it's basically Euclidean distance, but with this extra factor sigma in between that tries to weight different directions in the data space. And our goal is to learn sigma. So the method number 1, we call it explore. So I've showed it in one of the tables earlier. So here, of course, we still need some amount of data to learn it, but instead of asking a human to define a fair metric, which is very hard, so instead we can ask some annotator to label pairs of samples as comparable or incomparable. And then we will essentially fit a model that will find the sigma such that whenever the individuals are comparable, so they're fair, the fair distance between them is small. So again, example is this loan applicants with similar income such as Ryan and Tori. So what will happen in practice, the application for Ryan, application for Tari, and the expert can look at them and say whether they're comparable or not. And then sort of such kind of a data signal can be used to learn a fair metric. So another example is what we call a sort of a fair metric via a sensitive subspace. So we used it in this example with human names that I presented at the beginning of my talk. So as an input, we need, again, some human expertise to provide groups or groups of comparable samples. So once we have a group of comparable samples, such as names, so here we just used, we took word embeddings of popular baby names. That's all we needed to do. We just took a large, large set of names, and that's it. So because we consider all the names comparable, the idea is basically to use a principal component analysis, PCA, to extract the major directions of variation. So once we know the variation in the space of names, we essentially want to ignore any difference in that subspace when we compute the fair metric. So that's the main idea here. So, and these fair metric learning techniques, I use them throughout all the examples in this presentation. So they're quite effective and also quite easy to implement in practice. Okay, so here's a summary of our work in this direction. So over the past couple of years, so we were working on this topic quite extensively. And in addition to fair training methods that I've presented, there is and the fair metric learning methods, we also have methods for doing the same stuff as broader class of classifiers. So for example, gradient boosting. Then we can also do it with ranking. We also have methods for testing for individual fairness. So perhaps which is an important first step. So whenever we look at the machine learning model, before maybe jumping ahead and trying to fix it, we should probably check whether the model is actually unfair or not. So for that, we could use individual fairness testing. And then we have a post-processing method that we came up with recently. So that is maybe a first sort of short-term solution while we are trying to actually implement the training methods to correct the biases. There are also blog posts, just if you want to get more introductory material into this problem of algorithmic fairness. And my website is a great source if you want to find paper links. There are also videos that go into each topic a little bit deeper. I post some news updates there, and there are some links to the code as well. So please check it out. And finally, I would like to thank my collaborators. So from University of Michigan, from University of Constance, collaborators at IBM, and also at Wells Fargo. So all of them contributed to creation of the algorithms. They worked on visualization tools, on the fairness package that's currently being prepared, and so on. So thanks to them. And thanks to you for your attention. I'm happy to answer questions.
Thank you so much, Mikhail. It was such a great presentation. I think topics like this should be talked more, and really good to know that your company is creating a Python library that will make tools more accessible to everyone that it doesn't have time to do all this research. Thank you so much.
Thank you.
I see we already have a question, so I'll start with that one. Could you comment on the relationship between using training versus post-processing to achieve individual fairness? Are both approaches often needed in practice?
Yeah. So, well, post-processing, I think, is a very sort of easy thing to try out at first. So we already have a model. The model could be very complicated. Again, many components in it. So post-processing is very easy to try. So yeah, we still need sort of a fair metric to construct a graph, but otherwise it could be a black box model, and we can just see what it does. And in terms of effectiveness, sometimes actually it's even more effective than the sort of the training methods. But there is also a limitation. So post-processing is what people call a transductive learning. So we need to sort of know in advance what data set we're going to predict on. So then we can apply it. So because it's post-processing, right? So we have a test data set, we produce some predictions, then we modify them. Versus in-processing is, once we, once we've trained something, we can just start using it everywhere. So training is a better long-term solution, more reliable, versus post-processing is more like a very nice and easy to use like short-term solution.
Awesome, thank you so much. There was also a follow-up question on which one is eliminate more unfairness, and I think you already covered that. Thank you so much. We just got another question. So in your experience, how many subgroups are manageable for try to achieve fairness? 5, 10, 20?
Yes. So, I mean, well, when we work with individual fairness, we don't need to worry about subgroups. That's kind of the key. So we just try to achieve individual fairness because, as I mentioned, individual fairness considers almost every data point as a subgroup. So it's the most fine-grained definition that we could ever think of. And we don't need to explicitly define them. So we just go for individual fairness. We need a fair metric, but then we'll achieve subgroup fairness as well. Versus if you want to use group fairness, then we need to be more explicit about the subgroup definitions. And really, it's even if you just have a let's say gender and race, and you have you're not particularly careful, you just consider like 2 races, 2 genders, then it's already 4 subgroups. If you also consider intersectionality, and it's already not that trivial. I mean, that is doable, but going beyond that, it very quickly becomes really a lot of subgroups. You add another dimension, and now you have 8, and I don't think you can quite do like beyond 10. That's answering your question more directly.
Awesome. Thank you so much. So people, thank you. If you have any other question, please post it in the chat. We still have 5 minutes, so we can cover some other question. Meanwhile, I would like to ask myself a question, if you don't mind. So can you give us like a preview on what the Python library will help people do, measure fairness, help reducing it?
Yeah, so the idea of the Python library is to essentially just offer the functionalities that our algorithms offer, but in an easy way. So particularly the training methods, right? So far I've gave an example with this, sentiment classification. I gave some simulated examples for toxicity classification, occupation prediction. So eventually we want kind of doing all these experiments very easy. So the goal is to be, I don't know if we'll get there, but the goal is to be as nice as scikit-learn. If you're a Python user, if you're doing some data analysis with Python, I feel like scikit-learn is a really nice tool. It's a nicely sort of standardized, quite intuitive. So that's what we are shooting for. And so in terms of capability, yes, so we'll have training. So we'll have parametric learning. We'll have auditing or testing for violations of fairness, post-processing methods as well. So hopefully all of this will be supported, as well as different models. So maybe someone wants to train a deep neural network and someone wants to train like a random forest classifier or logistic regression. So we'll try to support as many of those as we can. Because currently we already have the algorithmic tools to do almost all of that. But it's, I understand that not everybody can just go and read the paper and spend a bunch of time re-implementing this. So this is quite a large amount of time commitment. So that's why we're trying to make it simpler.
Yeah, I think that's an awesome idea, because most of the time, especially in work environment, like they don't have maybe a research environment, they don't have time to go through the entire paper, and providing also a library of support to the paper, it's such an amazing thing.
Yeah, that's kind of why we started it, because I realized that when I talk to people doing more applied work, so we also work with, let's say, some researchers in IBM who work on healthcare. So they try to use maybe some of our auditing tools for, comparing like this methods that are used by cardiologists for like predicting the risk of atrial fibrillation, I believe. So yeah, but it's harder for them to just go through the paper and just throw it. So we help them to like implement the tools, maybe modify them a little bit to suit their needs better. And so just through all these experiences with people doing more applied work, I realized that we need to meet somewhere, right? They teach us about applications, and we need to also help them to use our algorithmic solutions.
True. I like the point that researcher and people that apply this concept need to meet somewhere, and the Python library is where usually people they meet. Yes. Okay, so thank you so much. Thank you so much for providing all these details. And I don't see any other question coming, so I think we can close it 1 minute early. So thank you so much again. Thank you so much for presenting to TMLS, and have a good rest of your day.
Thank you. Bye.